Okay, here's one of a couple review videos just on forces and determining net force. All right, so this would be a simpler one. We're just looking at forces that are already parallel to the x or y axes, nothing too complicated. All right, so let's say we have an object, like I have a box here, and then we got a couple people that might be, for some reason, pulling in different directions, like tug of war. And so I have a rope here, and this person's pulling with some force. So let's call this person A. This will be person B, and person A pulls so that there's a tension. We'll call tension A, and it's directed to the right. They're trying to pull the block across this surface of the ground. And then the other person over here on the left, person B, pulls with some force that makes so that there's a tension force B in this other rope attached to the box. All right, so we're not going to put any numbers in here. We'll just think about always using our free body diagrams and then talking about the total amount of force. So if I have a free body diagram for my box, I have a dot. I know this is on the earth. I'm going to have FG pointing straight down, so I can call that FG. And we need a mass for our box, so let's call it M. So that means my FG is equal to mg. If the box had a mass of 1/2 m, then FG would be 1/2 mg. The box is on the surface of the ground in green, so that's a surface. It's in contact with the object. That means we have a normal force. So the normal force, remember, is always perpendicular to the surface. Perpendicular to the surface is going to be vertical here, or perpendicular to the green line, the ground. So I've got normal force right there. When I have something just on this horizontal plane, on this horizontal ground line that's in green, and I have two forces that are pulling right or left or something like that, then you're not going to have any acceleration or anything happening vertically. So that's when we can say, okay, those must be equal. So Fn must be equal to mg. Those are balancing out. And we can only say that because we know A, let's say in the y direction, if I actually draw axes on here, I would call straight up and down the y-axis, then acceleration in the y-axis is 0. If that's the case, then those forces must be balanced. All right, then we have let's say person A is pulling more strongly. So that means tension A is going to be longer than tension B. And so the person on the left, person B, pulls less strongly. So there's less force of tension in the rope on the left. And remember, there are two different ropes here in my example. So they're two different tensions. It's possible they could be the same, but they'd still be two different ropes. So you can't say they're going to have the same tension unless you can prove it. So in this case, I'm stipulating that person A pulls more strongly. Therefore, the tension in A is going to be greater than the tension in B. So that's something I can add. We don't usually write this, but just to make sure it's very clear to everybody. Tension A, in my case, is greater than tension B because I said so, because the person A is pulling strongly. This is an example. If I put in the axis, the x-axis, since I called y the vertical axis, then the x-axis is going to be this horizontal one, like you're used to seeing it. All right, so when we go to say, all right, how can I find the net force? That's the left part of this sigma F equals ma equation. The left side here, that is net force. Net force equals mass times acceleration. Okay, so I'm going to end up rewriting this sigma F equals ma vertically, going down, and we just keep substituting stuff in. Now you can always look at F equals ma in the x direction, and you can look at it in the y direction. In this case, my x is the horizontal, parallel to the ground, and y is vertical, perpendicular to the ground. So if I'm looking in the x direction, it's convenient to put in a subscript to remind you that you're just doing it in that direction. You need to separate it. Okay, so there's sigma F in the x direction equals m times acceleration in the x, and sigma F in the y equals mass times acceleration in the y. You may have an acceleration in the x direction, but then no acceleration in the y direction. That'll actually be the case here. So I go and I look back at my free body diagram, and let's just talk about the y direction first. So I have normal force pointing straight up, Fg pointing straight down. I'm going to rewrite my sigma Fy equals may. I just come right down below that, and the net force is going to be the difference between these opposing forces. The normal force is going up, and gravitational force is going in the opposite direction. So they're opposing each other. If they're opposing each other, you're finding the difference. There should be a minus sign there. So if we call, it's arbitrary, but if we call up the positive direction, that's positive direction, then I'd have positive normal force minus Fg equals MAY. So what I've underlined right here in blue, that's another way of writing the net force in this particular case. You always start with sigma F for net force equals MA. And depending on the scenario, you replace sigma F with an expression that tells you the net force. You can see in the diagram that these are going to balance out because the acceleration vertically or in the y direction is 0. So I would say normal force minus Fg. This is like painstakingly step by step. Mass times 0 because acceleration in the y direction is 0. Okay, mass times 0 is 0. So normal force minus Fg equals mass times 0, which is 0. And so then we say normal force equals Fg. And then you could go on to substitute whatever the mass of the thing is. It happens just to be m times little g. That's Fg. So there's us showing the full thing for F equals ma in the y direction. If we go in the x direction, now we look at our purple arrows on the free body diagram. Sigma F in the x direction. That's what we're going to write first, just below, on the left side of our new equation. And I look at what's the larger force, TA or TB? TA, signified by a longer arrow, because I said pretend person A pulls more strongly. Okay, so call that direction where the stronger force is, just make that the positive direction. Because where the stronger force is, or where the net force is, that's going to be the direction of the acceleration and the direction of the net force. So it's more convenient to just call that the positive direction, usually. You can always change which direction is going to be positive, or you can always choose your own. Like if you want to the right to be negative, fine, do it. It doesn't matter, but you got to be consistent with it. You can't just change the directions in the middle of the problem. All right, so to the right's positive. So I'm doing that because TA is larger. And that way I can write TA minus TB. I write minus because they are in opposite directions. They're fighting against each other. All right, TB is pulling back against TA. So the total net force is going to be the difference between them. The net force is the difference between them because they're in opposite directions. They're the only forces horizontally, so I don't have any more forces to add or subtract. And that's going to be mass times acceleration in the x direction. All right, if I said something like solve for acceleration, well, you divide by m, right? TA minus TB over mass is going to be acceleration, and more specifically in the x direction. Okay? So there's a very simple way of looking at just finding net force with just a couple forces in opposite directions. Say we have the same box. All right, so I'll do a free body diagram in a second. Here's the ground, but let's say there's friction now. So let's say it's accelerating to the right, and so there's some tension force. Let's call it TA again. That's pulling it rightward, and then friction. Let's say this thing's already moving to the right, so its velocity is to the right. It's sliding along and it's speeding up. So then friction force, if it's moving, would be kinetic friction. It's Fk. And let's say there's some poor guy standing over here who's still trying to like stop the acceleration of this box. So he's grabbing onto a rope that's connected. So I would have another force. So say he's pulling this way, or just getting dragged, but he's still pulling on it. So he's planted his feet. He's trying to prevent the box from accelerating anymore. So there's still another force there that he's pulling with, another rope, TB. And we'll put our other person over here who's pulling with force that's equivalent to the force in the tension, TA. All right, so now if there's friction there and the thing's moving, it's accelerating to the right. If I do a free body diagram for that, I still have my normal force and gravitational force. There's Fg. Let's call the mass of our box is still m. So it's mg. Nothing's happening vertically, so normal force is up there and they're balancing out. I've got TA to the right just like I drew above, and now I'm saying TB is pulling back, but the thing's in motion now, so I've got some friction. I got to make sure I have, like I drew above, both my arrows leftwards should be parallel. We'll do it like that. because they have to point in the same direction. And then again, I can do sum of the forces in the x direction equals max, and sum of the forces in the y direction equals may. This may, I'm not going to write the whole thing out again, because you know normal force is going to be equal to mg. There's nothing happening there. So when acceleration is 0, you're just setting all the forces in one direction equal to all the forces in the other direction. All right, x direction, that's where we have something different. I'm going to call to the right positive, because I know that's the direction of the net force, because I said in the beginning of the problem the acceleration is to the right, so you know the net force is to the right. So I'm going to call that the positive direction. Take my larger force, TA, and subtract from it the forces in the opposite direction that are fighting against it. So there's TA minus FK minus tension B equals mass of our block times acceleration in the x direction. There's something else we can add here if we wanted to get a little more specific. Fk, this is one of our true statements we always know, is equal to mu k times the normal force. Okay, so maybe you substitute that in. A lot of the time, every time there's a friction problem, you're going to have to do that with me. So you've got TA minus, what's friction? Mu k times normal force, put it in there, minus tension B equals max. All right, well, we know the normal force. All right, so there's another thing from analyzing the y direction or y dimension, right? Analyzing that and saying, okay, the acceleration there is 0, therefore normal force equals Fg, and Fg is mg. You can substitute that in. So now you have TA minus mu k mg minus Tb equals max. And now it's just like, well, what are you asked to solve for? If you need to solve for A, the acceleration, you're just dividing by m, right? Because that's all you got to do to get A by itself. It's divide by m. Maybe we wanted to find the tension in string A or rope A. Then I would be adding those two terms on the left side, minus mu kmg and minus Tb. I'd be adding those to the other side to isolate Ta. So there's mass times acceleration in the x plus mu kmg plus Tb. Right? Or you whatever you're asked to solve for, you isolate it. Okay. I mean, that's really about it for just forces in one direction or the other, all parallel, nothing at a weird angle. Always remember that you need to look at F equals ma and look at it in both directions. And things can balance out like we have vertically here, in which case normal force is just equal to Fg. If I had another force pointing upwards, you know, like if I had somebody was lifting it a little bit with an applied force, and then you also still had the normal force, then we would say Fn, here's my new example, if we did that, then you'd say Fn plus Fa equals Fg. If there's still no acceleration vertically, so you're saying all the forces up balance with all the forces down. You can only do that if you know the acceleration in that direction is 0. Because if the acceleration is 0, then the net force is 0, then all the forces balance out. That is to say, all the forces upwards would have to balance with all the forces downwards. In our x direction, we have an unbalanced force, because I said in the example, person A pulls more strongly. So to find the net force, you would do this guy right here. Find the difference. Make the larger force positive, subtract the smaller force. That's the net force. Net force is sigma F, sum of all the forces.